Okay, so thanks, Judine, for the reminder to record. And if you want to disappear now and go dark and keep your hairstyle for yourself, you can go dark. So we want to look today with the idea of how do we deal with misconceptions? How do we change incorrect, right, concepts? So let me see if I can share screen here. And today I have several screens open. Oh, and what I will do, I will start with this thing first. Yes, before I get to the lesson itself, there's a related video that I will show you. It's about 6 minutes in all. Okay, I hope you are seeing my screen because I am not. Are you seeing my screen?
Yes, sir.
Okay, what were you seeing? I wasn't seeing anything. What were you seeing?
The entire screen, your desktop.
Right, that's what I wanted to see. I wanted you just to see this. Are you seeing explore your future?
Yes, sir.
All right, cool. So I want to share with you today, first of all, a couple of videos on what we call discrepant events, because discrepant events is one approach we can use to create conceptual change. So rather than talk about it first, I will make you look at this video here. It's 6 minutes, 51 seconds. We won't show the whole video, we'll skip parts. So looking at discrepant events. And after I'm finished, we're going to get to some explanation. So in between, I'll pause the video and take some feedback from you.
Explore Your Future STEM program. And this, of course, is Tootsie. Today is COA's Virtual Family Day. Throughout the day, we'll be featuring different activities from all of our different departments, such as the Family Resource Center. I will, of course, be doing a STEM activity, and I really hope that you enjoy it. It's going to look a little bit different as we will be doing 3 different types of discrepant events. A discrepant event is an occurrence that defies our understanding of the world by presenting unexpected outcomes. We usually use discrepant events in the classroom to engage students and grab their attention right away. Now we're going to do discrepant event number 1. So here.
Okay, so discrepant event number 1. And before we go further, let me play this little piece again and then I'll pause it. Listen for me, please, carefully. I'll ask you a question shortly.
I have a plastic Ziploc bag that has been sealed with water, and there's food coloring in the water to make it stand out a little bit more. I have a plate, and I have 2 sharp pencils. What I'm going to do is I'm going to poke the pencils through the bag where the water is.
All right, so she's going to push the pencils through the bag that contains water dyed blue. Question. Predict what you think will happen when she pushes the pencil through the bag. What do you think will happen?
Sir, I see it already. I know that trick, so I don't want to answer.
You see it already. Okay, thank you. Is that Andrine?
Yes, sir.
All right, thank you for that.
So anybody? Push the pencil, it might, create a hole because the liquid in it goes. Or as well as it might not, it might create a stopper at the same time.
Okay. All right. So if you had to pick one option, which one might you choose?
That the liquid might leak out.
Okay. All right. Thank you. So let's watch the video. So this is a thing too you can do with your students in science classes generally. Do a demonstration. It's often called POE, predict, observe, explain, POE. So you first of all ask them to predict what will happen. Then you carry out a demonstration and have the class, have the students observe. And then ask them to explain what they observed. So here again it is. She's going to push pencil through the bag. Does it leak? Does it not leak? Does it explode suddenly and water flies everywhere? Does it create a nice stream of water like a fountain and just leaks out slowly? What happens? Let's observe now.
I want you all to predict, what do you think is going to happen? Is the bag going to burst? Is it just going to leak? Or is the water going to stay inside? Let's make sure it's really sealed and let's find out. So I'm going to take the pencil and poke it through very quickly. There is pencil number 1. I'm gonna take the second pencil and do it again. See if my prediction holds true. And I poked it through. So 2 pencils have been poked through and none of them have leaked. As we can see from the plate, no water leaked out from the bag. This is
Okay, so no water has leaked out of the bag at all. Now, I guess if you have Ziploc bags that you can afford to spoil one, you can try it to see if that works. You can even try it maybe with a little plastic bag to see if it matters the thickness of the bag or not. But anybody think they can explain why this happened? Just curious. Okay, it sounds like no one wants to try, I guess. Okay, so here is the explanation. Listen carefully.
It's because plastic bags are made out of polymers that are made out of many molecules, are flexible and allow the stretchiness of this Ziploc bag material. When the pencil pokes through the Ziploc bag creates a watertight seal around the pencil and keeps the water from leaking outside of the bag. And that's for discrepant event number 2. So I have this little tea candle. I'm going to place it on the plate and I'm going to light it.
So she has lit.
All right. I have some of the blue
candle.
food coloring from the pencil discrepant event. So I'm going to pour it into the plate.
And she's pouring some water
Cover
around
the
the
bottom.
candle that is lit.
Make sure not to put out your candle. All right. Now I have this this glass cup. I'm going to place it over the candle. What do you think is going to happen to the water? Let's find out.
Okay, so she's going to place the glass over the candle that is lighting. What do you think you will observe? Unmute. What's that?
The water will move.
The water will move. Water will move where? How?
Around the glass.
Okay, it will move around the glass. Okay, so you will see it like circulating the gas, right? Surrounding, going around and around kind of thing. Okay, thank you. One other person at least. What do you think would happen?
Sir, could you repeat the question? I wasn't hearing.
Oh. All right, I will ask one of your classmates to repeat the question. So one of your classmates, please, just not get my voice only. Can you repeat the question, please, for Tanya? Tanya Lee.
So, sir, I want to know what will happen to the once she placed the glass over the candle, what will happen to the water?
Yes.
Sir, is it I'm not really so concerned about is it the liquid that you're concerned about, or the mere fact that the candle is lit and without oxygen, then the fire will go out? I don't know.
Okay, I mean, whatever observation. So you think that the candle will out?
Once there isn't sufficient, well, maybe there will be oxygen still under the cup. So
okay. So let us see then what happens. Oh, Judine, your hand is up, sis. Go ahead, please.
I'm assuming that it may turn vapor somewhat and moisten the walls of the glass.
Mm-hmm. Okay.
Yeah, that's my assumption.
Thanks for those answers. That is your prediction, what you think will happen. So let's watch, please, carefully. Hold on. Someone type something in the chat. Is that a guess the person is making here? Oh, Christian.
She said agreed. I don't know what she was agreeing to.
Okay, so let's watch.
As you can see, the flame on the candle went out and the water is rising into the...
Okay, so what do you notice happened? She has said it, but she spoke very low. What happened?
somewhat of a vacuum happen, something like that.
So the
Where the
flame
water-
went, the flame went out. The flame went out. It's always observation. And what happened to the water?
That the water is rising.
The water rose where?
Under
In
Under the glass.
the glass.
So inside the glass, the water level rose. So why do you think that happened now? Explanation. What caused that?
somebody else has something to do with pressure.
Yeah, physics people. What happened there? What happened? My physics peeps. Physics peep, quiet, quiet. Right, so let's not tell you what happens, but it has to do with pressure. You are right. Yes, go ahead.
I'm assuming, not a physics person, but I'm assuming that the flame, while it was there,
Mhm,
it actually helped to create like a suction,
mhm.
pulling the water inside. And when it went out, the water stopped being pulled into the glass.
Right, but why was the flame able to do that? By the way, who is speaking?
It was Jadine speaking.
Judine, all right. So it's a good answer. It's linked to the flame, but why was the flame able to do that? Yes?
I'm typing in the chat because my internet is in and out, so probably you guys won't hear me as clearly.
Okay, and that is who is speaking now?
That was Princess.
Oh, Princess. All right, all right. No problem. Okay, so let her explain, and then I will repeat if I need to. Listen carefully.
The cup. So I'm going to tilt
Before you play, sir,
to show you.
Mm-hmm.
Kristen, pause it, sir. Kristen said it was using up oxygen
Mm-hmm.
in the chat.
Okay. Yes, so that's very much close to the answer.
So continuing close to that, if it was using up oxygen
Mm-hmm.
and it created a suction, the space that the oxygen would have occupied, then the suction that it created would have allowed for the water to take up, for the water to come up underneath the cup to occupy the space of the oxygen that was used.
Okay, and who is giving me that answer? Judine?
Yes, sir.
All right, so that's a fantastic answer. So it has to do basically with that when the candle was being lit, as it burned, it used up oxygen. So the oxygen was used up, so that caused the pressure inside of the glass to drop relative to the pressure outside of the glass. And so that decrease in pressure inside the glass compared to what's outside resulted in a flow of water from outside the glass to inside to fill that vacuum created by the loss of oxygen. All right, so well, that's exactly what it is.
That most of the
Good job.
water has risen into the cup and the flame inside has gone out. This is because the flame uses all the oxygen up inside the cup, so that creates a low pressure environment, and the atmospheric pressure tries to compensate by making it equal. What happens is the cup creates a watertight seal, and due to the difference in pressure, the atmospheric pressure feels that it needs to even out. So then water rushes in, causing the pressure inside the cup and outside to be equal. Now for discrepant event number 3.
Last one.
So I have the plate from earlier and a new candle, and I'm gonna light the candle. I had to move Tootsie out for this event because I didn't want to hurt her little ears because it does get a little loud. So I have blown up a balloon. So I want you all to predict what's going to happen to the balloon when I put it over the flame.
Yes, so she's about to put a balloon over a flame. What will happen to the balloon?
So is she going to hold it over it?
Yes, she'll
Or just
hold the
rest
balloon.
it over it?
She'll hold the balloon over the flame, right above the flame. What will happen to the balloon? To be touching the flame.
I think it would cause the air inside of the balloon to gain some kinetic energy, I think. Something along that line.
And what will be the observation?
Not so sure about that part.
That's the part I want from you.
Balloon will burst, sir.
Balloon will burst. Anybody else?
Float.
Balloon it will float. So a couple people say so. Princess say burst, Christian say burst, and somebody say the balloon will float.
I'm thinking that if she didn't hold it over the flame immediately, then it would have, after it got some kinetic energy, it would have just raised in the air. But then I think, agreeing with Christian and Princess Ali, that it will burst.
Is it an empty balloon, sir?
Yes, just air is in it. It's not empty. There's air in it. All right, so watch me, please. Look what happens. Let's watch.
Your prediction. All right. So trigger warning if you guys are sensitive to loud noises. All right.
Everybody seen that?
Yes, sir.
So that balloon burst. Why did it burst? We're not finished with this yet. Why did it burst?
Because it has to do with the material that the balloon is made of.
Mm-hmm.
So because of the plastic balloon, when it goes into the flame or goes near the flame, it starts to deteriorate. That's how it bursts.
Okay, it starts to deteriorate. So the balloon starts to break down and deteriorate at the point that you apply heat. So it bursts. Because that point, I guess, will get weak by the flame, right? Heating it.
Mm.
Right. You also might have argued too from the perspective of it, well, the air got hot in the balloon, it expanded.
My hand up.
Whose hand is up? I'm not seeing any hand. Princess?
Princess, sir. You're kind of explaining what I have my hand up to say.
Go ahead, Princess. Sorry.
I was going to make reference to the specific heat capacity of air.
Mm-hmm.
And the change in the temperature of the air when it is placed close to the flame.
All right. Don't lose that. Keep that. What about the specific heat capacity of air? Is it low, very high?
It's very low.
Very low. So what does that mean?
Mm-hmm.
Don't require a lot of heat for it to change its temperature.
Sorry, can you repeat that first part?
It doesn't require
a lot of.
Right, I'm making sure you said don't require as opposed to does require. Okay, so it does not need much heat to change temperature. Okay, watch for me, please, because this is not finished yet. This is the next part of this that I think tonight you must try and get a balloon. Not tonight, the curfew soon coming anyway. I want to try this one weekend. This next part here. Watch it, please.
All right, so now we're gonna light the candle again. And now I have a balloon that is filled with water. So
this time balloon
swirl around
has
just to
water
show you
in
if
it.
there is water. You can hear it. All right, now I'm gonna place the balloon with the water over the flame. So what do you think is gonna happen?
Okay, what's gonna happen now? A balloon that has water in it, placed over the flame. What will happen? Just predict what happened.
Won't burst as quick as before with the air alone.
Okay, it wouldn't burst as quick as
It takes
before.
a longer time for this balloon to burst.
It will take what?
A longer time.
Longer time to burst, okay.
Right.
So the first one took maybe like 5 seconds. This one will take, what, I think, 15 seconds? Okay, next person.
Maybe it will expand, sir. I don't know.
Okay, we'll expand. That's okay. And I'm just saying to you, these are the kind of things we can do with students and ask them, hey, what do you think will happen if I do this? And sometimes, like she mentioned, we use these activities for engagement reasons. Students get excited. They say it's like magic. Other times you can tie it to a lesson that you are teaching specifically. Or in our case, we want to see how we can use discrepant events for bringing about conceptual change, for readjusting students' misconceptions. All right? So watch please what happens as she heats the balloon that is filled with water. flame is touching the balloon.
As you can see, the balloon does not pop and it leaves a little carbon trace here. So what's the science behind this? This is because water is a great conductor.
Right.
Yeah.
So I'll make a little pause here, right? That is part of the answer. She doesn't explain too well. Water is not a great conductor, but we'll talk more on that shortly. But she's right about something about water, but it's not as being a great conductor. But watch me, please.
And it soaks up the heat very readily. What happens is that, oops, I got some carbon on me. What happens is that as you place the balloon portion where the water is, the water acts as a conductor where the water at the bottom heats and then that water rises, because remember, heat rises, and the cooler water goes down, and this process repeats until the flame becomes too hot and the water is all warm, and eventually the balloon will...
Right. What do we call that process that she's describing there? Where the water gets hot and it rises and the cooler water comes down to replace that warm water. What is that process called? Physics people.
Conduction, sir.
Conduction.
Convection, sorry. Convection.
Convection, yes. Convection. So water has a high specific heat capacity, it's a great conductor. And because it has a high heat capacity, it has to absorb a lot of energy before the temperature changes. But also, as you heat the balloon at one point, the water that's hot rises, it gets less dense, and the cooler water sinks. And so you have this what's called conventional current established, circulating, cooling the balloon. But if you keep heating this balloon long enough, what happens eventually? If you will heat the balloon long enough, what happens eventually?
It will burst, sir.
Right, it will burst. She doesn't do that here, but she talks about it. Listen.
Pop. If I were to turn it to a portion where there wasn't water, the balloon would indeed pop because there isn't water there acting as a conductor. The carbon here just is a little smudge. If you get rid of it, you'll see that it didn't actually do anything to the balloon instead of leaving a gross black mark. I hope you enjoy viewing these discrepant events as much as I enjoy demonstrating them. If you decide to do it at home, please.
All right, so we'll make that stop here for now. So that was just discrepant event, and it will be mentioned later in class again as one of the ways you can help correct students' misconceptions, right? By asking them to predict what will happen if, and you as the teacher, the educator, you are going to do a particular activity and ask them to make a guess as to what they think will happen. And it's best if they do that in groups. Put them into groups and you let them discuss among themselves. As they discuss, you will see what it is they understand about science and science principles, right? So let me move on now to the PowerPoint that gets us to continue from last week's lesson. Princess, you did this with your class yesterday? For real, for real?
Yes, sir. We're looking at specific heat capacity.
Ah, oh, the topic, not the balloon.
I actually did the balloon experiment as well.
Okay, and it worked for you well?
Yes, sir.
Okay, nice. Big up yourself now, but not too big. Yeah? All right, thank you for sharing that, Princess. All right, so let me come back to look at where I want to start today's lesson back from. And then we'll end it just when we get to here. Right, so we're starting back at this point right here. So file, then we're going to share. Where is this now? Let me just hide this thing here that's blocking my view. Okay. So we know that in science, we have things that we call misconceptions. They're also called preconceptions. They're called naive conceptions. And they're also called alternate conceptions, meaning other ideas. So in yellow, I have highlighted an important distinction. It says that misconceptions are erroneous, they're false, they're incorrect, right? Ideas that students have about particular, in our case, science concepts. So misconceptions are erroneous, they are false, right? Ideas that students have about science concepts, science content. So we have what we call scientific ideas. These are the accepted ideas. They've been tried, various experiments have been done, and there is sort of a unanimous agreement, consensus, that this is correct, right? The misconceptions are alternative to science. There are other ideas put forward by people to explain certain phenomena that we observe in the real world. So as long as the idea is not consistent with what science says, it's regarded as a misconception. But these days we will call it preferably maybe an alternate conception or a preconception. One of those terms is what we use. We said last time that the ideas which are misconceptions or alternative conceptions, they come from many, many sources, right? From our family, from the community that we're coming from, religious beliefs, from the internet, okay? From books that we've read, from movies. That's where the ideas come from. Now, how do we bring about conceptual change? How can we do that? And there are many approaches that can be used. Here is this one. I'm showing to you as a fairly simple approach that you can use. So I'm showing you this one here. So one of the ways has to do with literally teaching. And so what you will do is that you will want to introduce the concept that you see here, right? And you tell students, and again, that was done last week. I'm just beginning here by a matter of review. And you tell students what the concept is, but also what it is not. So in science, the concept says mammals is the concept, or the concept is respiration. And you would tell them now, what is respiration? So you'll say the respiration is a process by which, right, living organisms obtain energy from their food, right? That is how you will define it, by saying what is respiration. So you tell them what it is, tell them, but also tell them what it is not. So respiration is a chemical process by which living things obtain energy from their food. That's what it is. But what is it not? Anybody want to tell me what respiration is not? And that is where you begin to help people unpack some of their misconceptions. Tell me something that respiration is not. Anybody, bio people, please contribute.
Inhaling and exhaling.
Sorry, didn't hear that.
Respiration is not inhaling and exhaling.
Okay, fine. So you have to tell the class that. Why are you saying that? Because you know as a teacher, thank you please for saying that students confuse respiration with breathing. So you tell them respiration is not breathing. It's not inhaling, exhaling. Rather, it's a chemical process that produces energy. But breathing is just a physical process, right? Inhaling, exhaling. What else is it not? Anybody else? Biology persons. So respiration is not breathing. What else is it not?
Inhaling oxygen and exhaling carbon dioxide.
Okay, if you want to get more specific now, it is not inhaling oxygen and exhaling carbon dioxide, right? That's good. You also can tell them as well too that it is not.
It's not the opposite of photosynthesis.
Thank you very much. I was just going to say that. I'm happy that you chipped in. It is not the opposite of photosynthesis. And I know sometimes we do that for the convenience of helping students understand, especially the chemical equation, right? but it is not the opposite of photosynthesis. That analogy is only useful for helping you get the equation. The reverse, it seems like, but it's really not just saying the opposite of photosynthesis. It is not. And also, right? So you want to make that clear. You may want to go on to say that there are different types of respiration. There's aerobic and anaerobic as part of your definition of understanding, right? But you want to make that clear. Now, you may also want to mention, sometimes we do this, an analogy, but we need to be careful using analogies, because analogies sometimes students incompletely understand the analogy and they think it's the same thing. So you can tell them that respiration is similar to a process that we call burning, or in chemistry, you say combustion. Similar to, not the same thing. How is it similar? Similar because burning will produce energy from food source. And you can show them, if I take a peanut in the lab, I can light it on fire, it will burn. And the heat from the peanut, I can use that to heat some water and see a rise in temperature. So burning can produce energy. In a similar way, respiration will produce energy. The difference, however, is that burning will produce all the energy all at once. But respiration, the energy is released incrementally, just as much as you need. If the body were to take your massive lunch that you had today and convert it into energy right away in one step, you will spontaneously catch fire and combust. You will burn up, literally. But there are enzymes that control the respiration process so that the energy is released slowly. All the energy from the food is not released in an instant, in 1 minute, in 2 minutes. If that happened, every time you eat, as if that's possible, you will die. Of course, you can't die many times over, but I'm just saying to you, right? So respiration is a energy releasing process, but the process is very much controlled. There are enzymes that control that process. Burning is like that, energy released from food, but it happens from fuel, but it happens instantly. All the energy is released. It is not controlled, not a controlled process. And the fact is, because of respiration processes occurring as well, is one of the ways that we can help, along, of course, with other mechanisms involving centers in the brain that maintains body temperature, right? So it needs to have respiration sped up or slow down. So if you're very cold, respiration will speed up to produce more energy, right? And if you're very, very hot, you need to slow it down so you don't keep overheating. And that's heating with an H. Yes, this is my popular Jamaican joke. All right, so you want to tell them what the concept is. Let's take another example. Let's say we're doing chemistry, and let's think, say, of a molecule and a compound. And let's suppose we want to define the term molecule, right? So the concept we're teaching is molecules. And you want to define what that is. So you define a molecule. Anybody here in chemistry, when we want to define the term molecule? Okay, we are so shy people. So molecules basically are made by chemically combining 2 or more atoms. Okay, it's a chemical combination of 2 or more atoms. So if I combine atoms of hydrogen, I will make the molecule hydrogen. If I combine, or I can make ozone if I combine 3 atoms, right? If I combine the molecules carbon and oxygen, I can make carbon monoxide or carbon dioxide. So molecules are made by atoms combining. And it's a chemical process. So it's like, bonding, spoken about bonding. And when you make molecules, what you have really is covalent bonding of atoms. So molecules you form by covalently bonding atoms. That's how you form molecules. Now, compounds, on the other hand, are different, right? So CO2 is a molecule, but CO2 is also a compound. So what we see here is that molecules can be compounds, but not all compounds are molecules. So for example, sodium chloride, calcium carbonate, they are compounds. They're not molecules. Why? Because calcium carbonate and sodium chloride are ionic substances. And to be a molecule, you need to combine atoms via covalent bonding, not ionic bonding, right? Whereas compounds, of course, simply means that you can be combining elements. They can be ions or atoms that are chemically bonded to make compounds. So again, you define the term molecule and you give examples: oxygen molecule, methane molecule, right? Glucose molecule, you define that. You also want to say that some molecules can be compounds, but not all molecules are compounds. And you want to talk about how compounds different from molecule. Okay, so that is an important thing you want to talk about. So you want to define the concept, tell them what it is, but also tell them what it is not. Okay, molecules are not atoms, because molecules are comprised of atoms, but they themselves are not atoms, because it combines atoms to make them, right? So they are chemically combined. All right, but again, and then having done that, in physics, someone wants to give me a physics concept?
So before we reach the physics concept, with the same molecule and compound
Compounds, yeah.
scenario, when we are referring to molecules as compound, we would say covalent compounds
Yes, covalent,
instead
yes.
of just saying compounds.
Compounds,
only.
yes, thank you. Thank you very much. That's useful. Right, so they are covalent compounds, right? And again, not all molecules per se are compounds, because oxygen, O2, is just a molecule. To be a compound, you have to have different elements combining chemically. So O2 or O3 or H2, right? While they're molecules, they're not compounds. Yes, and they're combined, they are combined covalently, but it's just one type of atom combining. You have to have at least two different atoms combining for the molecule form to be classified as a compound. So these are the kind of discussions you want to have and give examples. I know very often as teachers, we are so concerned with the syllabus completion that we don't spend enough time developing the concept, what it is not. And then later on, it comes back to cause a problem. So students, for example, later on you do moles and you ask them, calculate the number of moles of hydrogen. I keep reminding students, whenever a chemist says hydrogen, we mean the molecule H2, because the atoms don't exist by themselves. They exist, right, as diatomic molecules, hydrogen, likewise oxygen, right? So they have to understand that when I call a compound just as nitrogen, what I really mean is N2. I don't mean the atom. If I meant the atom, I will say nitrogen atom. So you have to kind of help students understand concepts and give examples, give non-examples. And then if you can, make the concept visible by having them, if possible, build a model so that the concept can be visualized, right? If possible, have them build models. So in chemistry, they can build models of atoms and molecules. They can build sodium chloride. They can build molecule of glucose, you know, molecules like graphite. They can build models. You're doing respiration. A model will be difficult to be built there, but you have to get them to understand that respiration happens inside of cells. Yeah, inside of cells. So that's important, that respiration happens inside of cells within something called a mitochondria you know, that's kind of, because the mitochondria, that's what its purpose is to produce energy for the cells. So you're gonna talk about what's happening inside of the cell. And maybe you can draw the cell, you know, show them a structure that you call the mitochondria and say, hey, that is where this process takes place. So they are learning to make an abstract concept like respiration visual, because you start by drawing a cell and you show them where inside the cell this process takes place. All right. And if depending upon the level, you can get the whole idea of the ATP breaking down to ADP and so on. But if not, just mention that it happens inside of cells. So we typically call it cellular respiration happening inside of cells. Okay. And then of course there are several enzymes that control the particular process. So it's not a one step, you know, there are several different steps in the process. So you can build models if you can, or if not, find a good video online with some animation stuff to show them what is happening so they can visualize the process. Beyond that, you also can draw concept maps. So they're making connections between the concepts that they've heard so that the word atom, molecule, compound, how are these terms related? Yeah, draw me a map to show your understanding of the concepts. Which term is a broader, inclusive concept? Which is a more specific concept? Give me examples of the different concepts. So a concept map is a nice way for you to visualize their understanding of particular concepts. Okay, so that is one approach you can take. Define the concept, tell them what it is and what it is not. Make the concept, if possible, visible by having them build a model of the particular concept, if possible. And if not possible, then certainly get them to draw concept maps showing how the various concepts are related. Okay? Any questions? I'll pause here before I move on. Any questions?
No, sir. Can continue.
All right. Blessings. So again, this is another approach that we can take here. It's very similar to the last one. A few minor differences. It starts by defining the concept, same way. Having defined the concept, you explain the terms. So last time we spoke with the example of photosynthesis as a process whereby, you know, plants use carbon dioxide and water in the presence of sunlight and chlorophyll to make, say, glucose, if you want to say food with some level, fine, and oxygen. You want to be able to go back to the definition and look at the different terms in the definition. We say that pressure is force acting per unit area. What does that mean? You know, pressure is equal to force over area. What does that mean? Give me some examples. So when I taught physics years ago, I would tell students, for example, you know, which do you think you will feel more pain from? A JUTC bus passing over your toe, or a lady in stiletto heels walking on your toe? Which one do you think will hurt more?
The heel, sir.
The heel, yeah. And the issue has to do with pressure, right? Because the heel is so tiny, the area is small, so the pressure is the force divided by the area. And that is why, for example, and I saw students as well to try that back in my class, I would take a pencil like this, and I'll call up somebody in the class. I say, look, using this eraser here for me, please, this eraser, as you can see here on the pencil, I hope you can see it. Push this pencil for me into my hand, you know, push it into my hand. Right? Push it, come. Nobody's stronger here. Get someone stronger. Push it into my hand, or the palm of my hand. Push it in. Push it. Whichever part you can handle pain better, push it in. So that's all you can do. Can't go further? I said, no, sir. It's all right. Now, do you think if I get a needle or a pin and I ask you to do that, do you think you will struggle as much? They said, no, sir. And I say, why? Because a pin point has a small area. All right, so they understand that pressure is a function of those particular things. And that is why, have you heard of this thing called snowshoes? I know we're not in a cold country per se, but maybe you watch movies and so on. Have you ever heard of snowshoes?
Yes, sir.
Okay, do you know what they look like?
So they're like boots attached to something else, some form of metal or something so that you can walk properly in the snow.
Okay. And the thing they're attached to, what does that thing look like? That's the main thing. What does that thing look like?
Sir,
Is
not
it-
quite sure, but I know like the front part is kind of pointy.
All right, but the soles of what it is, it's normally broad, spread out, right? It's broad and spread out. You know, for example, I don't know if any of you had that growing up. When you were small, if you're walking in an area and the area feels kind of like swampy, kind of mushy, how do we walk when we find the area feels swampy and mushy? What do we tend to do as people? An area is waterlogged, and you step in it and you realize it's kind of waterlogged. How do we proceed to walk?
Tiptoe.
Yeah.
We tiptoe.
But does that make sense?
Of course, sir, the whole of your foot now go wet up, so it makes sense.
But
Or
still,
you try find one dry part to put your foot.
But when you walk
it makes
tiptoe,
sense, yes, but sir, when we step on our toes, they're putting all of the pressure on our toes.
precisely. So it means that that toe will sink further down into the soft ground.
Yes, sir. The toe is sacrificed to the rest of your foot.
Whereas if you could possibly keep your walking normal, you could even spread the toes them out wide as possible, and you can walk, it will be a lot easier. So for example, if you're on snow, the snowshoes that even the Eskimos will use, they're like tennis rackets, broad and spread out, so that in the soft snow, you don't sink down into the snow because you're applying less pressure the broader the air is spread out, right? And I know firsthand, I had a minibus many years ago back in Grenada, pass over my toe in the market, waiting on a bus to go home one time. I guess I was chatting, wasn't paying attention, and I guess the driver careless as well too, passed over my toe. You know, it was a little painful, but not as much. Whereas any regular female stepping on your toe with and you have no shoes on, that will hurt like crazy. Yeah. Okay, but that's the idea. So define the concept, clarify the terms in the concept. Then you want to explain the attributes of the concept. So let's take, again, we've done this over and over, something like insects or mammals. So let's do mammals. What is a mammal? Anybody? Biology person. What's a mammal?
We have some animals that have mammalian gland can give suck to their youngs.
Okay, that's fine. And you have to explain what you mean by mammalian glands. Or you meant to say mammary glands, possibly? Yeah, they have mammary glands. So you need to explain what are mammary glands? Anybody?
Glands that are able to produce milk to
Okay,
facilitate the sucking of the young.
Okay, so quick question here, you know. Are males mammals?
Yes, we do have males that are mammals. However, it's more a characteristic of the females because they are the ones who generally have to produce either the egg or carry the child.
Right, so see all these kinds of things, as you explain the concept, you want to clarify. Understand me? Or a child must start to wonder, wait a minute, that means that only females can be mammals then. Males can be mammals because if males don't breastfeed, males must not be. You have to explain all of these things, and right? So explain the terms in the concept. Explain the features. So mammals, yes. The females, because when I learned this in primary school, the teacher only told me this, that mammals, we said, give suck to the young. Were you told the females or you just told mammals? What were you told? Okay, people are not hearing me clearly.
I don't remember that from primary school.
Oh, seriously? I recall it, the amount of licks, but anyway. So, and you want to mention the key features. So to be a mammal, okay, yes. Giving suck to the young, okay, fine. What else is important to be a mammal?
Warm-blooded.
Warm-blooded. Again, you have to explain. Does that mean that the blood warm?
No,
Because
they're
that's
able to produce their own body heat because we
right.
have dolphins that are mammals, so they
Right.
live in water.
So they're able to regulate their body temperature. So that's the idea. We normally call it homeothermic, from the idea of homeostasis, the idea that they can keep their body temperatures constant. So regardless of the environment, and that's why, for example, lizards, for example, are not mammals. When it gets very, very hot, what do lizards do?
I think they hibernate.
I don't know if hibernate is the right term. Hibernate is a term we associate with long sleep during cold months. So you're onto something, but it's not hibernate.
Ventilate.
Can you repeat, please?
Can they open up their mouth, sir? Like how dogs
Oh,
pant.
ventilate. Okay, so right. So maybe like it gets very hot, they might do that. And again, they will, if it's very, really, really hot, they will seek shelter or shade under a stone or somewhere. And if it's getting cooler and they find their body temperature dropping too much, they'll come outside on top of a stone to be clearly visible to get absorb the heat from the sun. Now, it must be difficult that your environment makes your temperature change. You have no control over that temperature. So things like turtles and lizards and so on, they need to move. So you know how we can go out in the sun and play football for 3 hours straight and our blood temperature stay perfectly the same? You can be in an AC car, AC building 3-4 hours, and your blood temperature don't drop down to the temperature of the room, 18 degrees Celsius AC setting. Your body temperature remains the same, roughly 36 point somebody, 35 point something, right? It's because we have the ability to do that. That is mammals. And then we see that mammals also have hair or fur covering their skin. Okay, that's, again, so we speak to the features, the characteristics, but we bear in mind that there are always a little bit of exceptions here and there. And we give examples of mammals. So you have mammals in sea, mammals on land, and mammals in the air, like bats. Because a child might see a bat as a bird, but no, a bat isn't a bird. Birds are different. Birds have feathers. Bats don't have feathers. Bats have fur, okay, / hair covering their skin. So we have to show students as we deal with the concept, define it, give examples of the concept, give non-examples of the concept, explain the defining features. So I'm looking at an atom or a molecule. I have to define it. I have to be very, very clear on non-examples of molecules. I'll give ions as an example, of molecules. I will give your ionic compounds and so on, right? You have to give examples and explain the main features. Also, like the chemistry one on atoms. Atoms, to be an atom, require you to have equal amounts of protons and electrons to be an atom. If those numbers are not equal, that's not an atom. It is something else. All right? So we have to take our time. And I know we take it for granted sometimes in teaching that students know these things already. Doesn't mean so. We all have these misconceptions that we carry through from primary school, if you were in primary school like I did, or if you were in prep school, maybe some of you in here may have gone to prep school, you would have had that kind of conception being incorrect from way back then. Okay. And this is the same thing. You want to just provide examples and ask students to classify them. So you provide lots of examples. So you're doing chemistry atoms, provide examples of atoms, cations, anions, compounds, and ask them, identify the ones that are atoms. Put them for me in a group, because you want to ensure that they can understand which ones are atoms. Pick out for me from this group here, the ones that are mammals, and you give them some pictures to classify them, to ensure that they understand the idea of what mammals. Okay. So conceptual change really involves that bold stuff here, involves teaching that tries to shift what the individual know, right? So because people come into classrooms knowing things, they have ideas from TV, from internet, from family. And in conceptual change, you want to try to reverse, to modify the understanding that they have. You want to shift that understanding. You want to get them to, if you can put off, you might say discard the non-scientific explanations and accept one that is more scientifically plausible, feasible, okay? And it says conceptual change, the last bullet point here, can be facilitated through critical thinking. And that is why today I began with the example of the predict, observe, explain, right? Can you try to explain why the water rushed inside of the glass that was covered when the flame was on? Why the water rushed inside? What was happening there? Why did the balloon with some water in it not burst? Okay, thinking about it. It is not just copying notes. Copying notes, and I'll tell students all the time like that. Do not be too quick on copying notes, or you have a book full of notes, but still no understanding. So write into your notebook that which you understand. You got to think about it critically, right? Question everything. Do not just accept because sir says so, miss says so, that's what it is, right? Encourage them to think, your students, that is. And so in conceptual change, you're trying to develop ideas that are different from those that you held once as a naive conception or a preconception. You want to do that, all right? And it says, when a student understands a concept really well, they can think with the concept, they can use it in what we call novel areas, apply it even outside of the context where they learned it. They can restate the concept in their own words. They don't need to write back sir words or miss words. When people are swatting off definitions, it's because they have no idea what it is that sir said or miss said. They are struggling to put it back in their own words because the concept never took hold. Can they restate it? Can they reword it? Can they use another analogy in place of the concept? So it's like how I spoke about earlier, respiration being similar to that of burning. Can you find an analogy? Or I think it was Danique some weeks ago said that somebody in her school, a student in one of her classes, was saying that the cell can be seen like as what you were saying, police.
No, sir, the security guard.
Security guard,
So they
okay,
were
was the
using
police.
the analogy of the school system to break down what a cell is and the different organisms inside of the cell.
So they were comparing, right? So what she was saying is that they were comparing the cell to your school plant, basically. So the school plant, the physical school, is like the cell. And the same way in the cell, you have different, you have security in the school system. What is the security component of the cell? So analogies can be used, but be careful when you use analogy, let the students know this is only an analogy. I'm just drawing a comparison. The cell, you know, don't have security. Years ago in primary school, I learned of tooth decay. And they use an analogy for tooth decay. Anybody can tell what analogy you think they use for tooth decay to teach it?
Rotten teeth.
Okay, rotting teeth, yes. But what do you think they use at the time? Say I must have been like maybe 9 years old, could be 8 years old, I'm not certain, in that area. And in a book I was reading, trying to explain, okay, what do we know? What are we told causes tooth decay? What causes it?
Sweets.
Sugar.
Sweets. But what about sugary and what happens to those sugary food?
It's sticky.
Right, it gets converted into acids, right? By usually by bacteria and so on that live in our mouths, right? So that's why you have to brush your teeth and all of that kind of stuff. But anyway, in that book, they showed me tooth decay were being caused by germs. They use the term then, they didn't say bacteria and so on, they said germs. And these germs were represented as being little men with chisels and hammer, yeah, knocking away at the tooth. And I was swear in my mind that that's what germs would look like, little men in your mouth, drilling holes into the tooth. I was not told this was only an analogy. It's just trying to represent the information. It is not till I got into high school many years later, not like first form, second form, like fourth form, that I finally understood that, wait, now, there were no little men living in our mouth. I honestly thought they were germs were like little men, right? So when you share analogies with students, caution them, please, that in the exam, they must not write back the analogy and say that, you know, a cell has a security, you know, and there is a nurse and so on. They have to use the technical terms back. So the analogy is to help you understand it. And having understood it now, can you tell me back in your own words without using the analogy? Also, you can have students build mental, but also physical models of the concept. If they understand a concept, they can represent it in their mind. They can think about it. They can draw diagrams that represent it. They can build a model to represent this particular concept. So all of those things are things we can do to help facilitate conceptual change. And as we get to the ending here, in order for a student to change their initial ideas, their other conception, they have to become convinced that what they now know and they've held to be true for years, they have to become convinced that this is incorrect. To just tell the child that that view is a wrong view wouldn't help them change it. You know, when people doubt you, do not make you hold more fast to what you believe? Yes? Tell me about your experience. Hello? Do we have anybody home? Yep, we have people home. I'm not
We're here, sir.
You
I
sure?
really, yes, sir. Yes, sir, we're here.
Okay, somebody was saying, I really something.
I was saying I really don't pay anybody any mind. So I just do what I want to do. I don't really pay attention to negative talks and those things. So it does nothing to me.
Well, that is you, the adult. But what about you, the student? And you are told that that idea is wrong. It is not true at all.
I don't remember that. That was a lot, donkey years ago. I really don't remember. I'd have to think long and hard about it.
All right, all right. I like the way you guys talk about donkey years ago as if you guys are so old, but anyway, yeah. All right, okay, appreciate that. So, but anyway, you have to convince the learner, the student, that the idea they currently hold is incomplete, it's incorrect, right? It is not consistent with what science now knows this to be. So you have to say, hey, this idea, and they have to release it, right? You cannot make them, they will become convinced that the scientific explanation makes the most sense, right? You can't just say that your idea is foolish and move on. All right, so there are several things that we can do, and some of this you can read on your own time, but you have to you have to be able to get the students' misconceptions to be brought to the surface, what we call diagnosing their misconceptions. So step one, as well too, another approach, you have to diagnose the misconception first of all, right? And then you have to provide for them some kind of discrepant event scenario in which they're going to do an experiment and they're going to get some information, some data that is contradictory to what they were expecting to happen. because what they thought would happen didn't happen. So you heat a balloon, it should burst. Heat the second time around and it doesn't burst. Okay, this is interesting. Yeah. So what is happening? They have to be able to find the gaps in the knowledge with the teacher's help and be willing to make an adjustment to what they know. All right. Again, you can read some of that here. I want to move on to this lesson. So it's a constructivist lesson, and that is a lesson that you can write. It's a lesson plan. So you can do the things I said before, in which you can define a concept, right? You can give examples and non-examples of the concept. You can explain key terms in the definition, okay? You can try to have them make a model of the concept if it's abstract. These are all things that you can do to bring about conceptual change. This last one here by Driver is an approach to conceptual change that is tied to the constructivist lesson plan. And he has several steps, about 6 or so steps, and then we'll come to the end of that. So he has these different steps for the lesson. This diagram here, I know you cannot see it. So these steps, I will show you them on the next slide, one by one. How do we teach for conceptual change? Another approach by doing a lesson plan, okay? So the first part in Driver's model is what he calls here orientation. So this top up here, orientation. What do you think is the orientation phase of the lesson? Just ask you. What happens in orientation?
Introduction.
Yeah, what happens? What happens there? What happens?
The engagement phase.
What happens there?
You catch the students' attention.
Okay.
Get them ready for the lesson.
Okay, fine. So what I want to make you see is that what Driver is saying is nothing that you don't know already. Watch for me, please. So in the orientation phase, you want to introduce students to the concept that they'll be studying. All right? It is similar to, as Danica, I think it was her voice I heard, the engagement phase of the lesson. So you introduce the concept, you do something that stimulates interest to focus on the topic. You may ask a question, may do a demonstration, watch a short film, 2 to 3 minutes long, right? Ask a riddle, something to get them ready for class. Orientation phase. The second phase is called elicitation of ideas. What do you think happens in that phase called elicitation? Right, people, what happens?
It's to know what students are thinking, I think.
What do you do there?
Questioning.
Okay. So that is where you try to see what students know. Okay. So you can ask them some questions as a whole class. You can put them into groups, small groups of 4s and 5s, right? In which you are going to brainstorm. But you want to hear from the students what they know about this topic, because you cannot try to teach, to change a concept if you don't know what the concept is. So you have to have the students share what they know about the topic. Interview, right? Maybe do diagnostic tests. Maybe they complete a concept map, right? Whatever it is, you have to get from the students what it is they know about topic X. What do they know already about this concept? Next, if we go back to Driver, Driver says next, and Driver says after we do the ideas and we get it from them, the bulk of what happens next, he says, goes to now clarification and exchange. So if we come on here, it's a big part here that he calls restructuring the idea. See that whole phase there, that big box, the long rectangular box there? Restructuring of ideas. That is when now, having diagnosed the alternate conception, you are going to try to have them restructure the idea. And again, you can do that in different ways. We talk about discrepant events. We talk about telling them what the concept is, examples, non-examples, building models of the concept, right? Doing these concept maps, but you have to begin to help them restructure the ideas that they have in their head. And very often, some kind of hands-on activity could be useful. Okay, some kind of hands-on activity, if it's possible. Because you know, there's somebody who says that, and I don't recall the exact quote now, but the idea is that we remember a lot more of what we do than what we're told. So you have to get them involved in some activity, whether it's building a model, you know, whether it's having discussion with people in groups, but you have to get them to begin to discuss what it is that they know and how this might be incorrect. And then you have this part here called a discrepant event part, where you show them a video, you do an experiment that causes them to begin to question what they believe to be true all of this time. You know, so it's like how you will feel a piece of metal and it feels cold, and you feel a piece of stick and it feels warm, so to speak, room temperature. And you ask them, based upon the way they feel, which one do you think is colder? If I were to measure the temperature of these two pieces of stuff, the temperature of the piece of metal or the temperature of the piece of stick, which one do you think will have a higher temperature? And the child might likely say, well, the piece of stick because it feels warmer. And you do it and you realize, wow, they have the same temperature. Okay. So how do I explain then that something feels cold, the other one feels warm, yet the two things have the same temperature? You know? And that those discrepant events is what begins to help the child realize that my understanding of temperature, therefore, seemed incomplete. Right? I obviously have some misconceptions. I'm going to realize that I can't use my senses only for judging temperature. Right? So that kind of thing is what you will do there. And then they have to begin to restructure. So you as a teacher have to provide what we call a scaffolding. You're providing support so that they can move from where they are to where they need to be. And the restructuring of the ideas take a while. It requires students to talk about it, to read about it, right? To do seat work in the class, so that they can then begin to articulate. And once the idea is restructured, you ask them, you know, please explain to me what is respiration, or what is photosynthesis, right? Or what is temperature? What is heat? Right? Those kinds of things. What is a molecule? What's an atom? What's a compound? Have them begin to use the terms as they speak and tell them to write you definitions. Tell them to give you examples and non-examples, other examples other than the one that you gave them in class. Can they do that? Right? So it's all part of restructuring the ideas that they have. And then lastly, you give some kind of test because you want to check. So like in your 5E model, you want to check what it is that they know. So you give a test now to check that they have the correct understanding. Okay. So that basically is where that is at here. I will stop here for now. And I am going to take a few questions, a few comments. Let's talk in particular about what you're doing with your students and your assignment. So anybody wants to go first? I would suggest it's your advantage to go first, since everybody can't speak. Wow. Yes, Andrine.
So many misconceptions. I'm not sure what to choose. I would like you to assist me in my topic.
Well, I'm sorry, I can't choose the topic for you.
No, not to choose. Just to probably just give you the ideas and to say if there are misconceptions, as based on the one that you listed in the assignment, they are not my topics based on what subject I teach.
No, fine. Because I tend to speak a lot more from my background, from my context. I know you agricultural science, so talk to me about yours.
All right, one of the misconception, and I think other person in the class may have it too, that brown eggs are healthier than white eggs. I don't know if that's a misconception, and that can be.
Yeah, I think there's a general thing and I have, because I've been here now for the last 12 years, I've come to believe, so I tend to prefer brown eggs. I don't know if it's a matter of health, but I just prefer. So if I'm buying the eggs and they're white, I will only buy them if there are no brown ones.
Sir, it's just culture.
Maybe
They're
it
the
is
same.
culture.
It's the same nutritional value, and there's no different. There's a breed of birds. Brown egg, brown bird, where brown lay brown eggs, and a white breed.
Right.
That's a different breed.
Is it also tied as well to the diet as well? So the color of the shells?
It didn't have anything to. No, there's a breed of animal. The
Are
breed.
you sure, miss?
Sir.
Are you sure?
Yes, sir. It's the breed.
Because if I look up something and I find it in a.
Well, based on what I was learning, it's just a breed. I will come on to health value. White egg or brown egg shell doesn't have anything to do. Another misconception, I'm not sure if most persons believe that organic farming is all better organic.
Better how?
Because most people have a notion that when you do organic farming, you use a lot of only organic fertilizer and organic chemical. So persons tend to go to the organic way because it's healthier. So that's one of the misconceptions, because a lot of persons they probably may use organic fertilizer, but they may use inorganic pesticide. So I'm not sure if the egg one, I'm to stick to the egg. And my students, they are more debating on the egg, and they have more arguments when it comes to the egg.
Right, because you want to do something that is relevant to your context.
Both of them are relevant to my context.
No, when I say relevant to your context, in terms of the particular group of students that you have, you are telling me that you find that you get more contentions with the issue of the egg.
Yes.
So your current context suggests that that may be the way for you to go, because that is what your students are, discussing a whole lot now. So you may want to go that approach because it's more relevant at this point. So you may want to. But again, you look in the literature and see what comes up, because here's what I did agricultural science myself as a student, and truth be told, because I did biology as well, I found some of it very easy. So in agricultural science, you can also speak the same idea too of respiration and photosynthesis, right? That misconception of the processes happen in both. Understand? Because agricultural science involves plants as well too. And
yeah, I'm doing photosynthesis too.
Right. And so not because it's agriculture means say must look at livestock rearing.
No, I know, sir. I'm doing, because it's not agri I teach environmental science too.
Right. So in environmental science as well too, you have to see, is there any misconception that people have to in that regard? Or so you can find something. And again, like I said, you go online and type in misconceptions in.
Yes, sir. Yeah? That's what I'm doing.
And see what comes up. That's what you're doing. That is what you should have.
No, so, I've done that. I have all the topics already. I have a lot of topics.
Okay, right. So just pick one. Very easy.
Right.
Pick, and hear what? It don't matter which one you pick. Like I explained to you last class, this is not a master's thesis you're doing or a PhD thesis. This is a part of an assignment, right? It's not your whole grade. So don't feel that the thing you're researching must be life-changing, earth-shattering, groundbreaking. No. It's just about the process you go through to identify misconceptions, to say what the correct conception is, and to begin to help students try to change it. That's all it is. It's just a process, right? So don't think that it has to be this extremely groundbreaking work you are doing. Not, if you want to do that, you can, but really and truly, that's not what this course is for, right? It's to get practice that later on, you can take that and say, let me apply that to my class, okay? Because generally as teachers, we don't do research in our classes. We see misconceptions as well. We see weaknesses, but I don't know if we really try hard to fix the problems we see. I think sometimes we're overwhelmed by the classes being so large, you know, we just really, and the syllabus to be completed, you know, it's like, all right, you know what, maybe closer to the exam, I'll come back and fix those. But for now, we'll have to move on, yeah? Because the syllabus needs to finish. So I know you said, Matthew, you didn't quite get this topic, you know, but we'll come back to it. You know what, maybe see me after school or at break time. We can talk about it. And that's kind of how we do it. We don't try within the class context, even if it's next week, come back and try to systematically try to treat with the misconceptions. Okay, so Andrine, I think you are settled on how to get your misconception. Anybody want to share with me what approach you think might work in remedying your misconception, the one that you have in mind? Tell me how might you go about fixing it. Let's talk about that. It looks like today I will let you off early if you participate. So you could go home in the next 15 minutes. You could go home in 15 minutes, but I have to hear participation. All right, so apparently I gather that people have not begun assignment 2 then.
Sir, it's just that I don't think everybody has got to that point.
Okay, they're not at that point yet. Well, those who are at that point, Mel, you were going to say something?
Sir, I've been looking at some topics.
Oh, you're still early in the process, still looking at topics. All right, no problem. Haven't decided an approach.
Looking as well. I'm wondering if my one is too short.
Tell me.
I was looking at formulas because we have problems with students writing incorrect formulas and classifying anions as, for example, the halogens as halogens instead of halide ions. So I can give them examples of correct formulas and incorrect formulas and show them different formulas in equation and maybe it will throw them off if the formula is incorrect when they are balancing equation and finding mole ratios and all of that. But I don't know if it is too short. I don't know.
You're wondering if it is too short. But again, did you double check to ensure that that is a problem area held by students in chemistry?
Yes, sir. I read the report, CSEC reports. It's a problem that is always there from 2004, right?
So why are you thinking it is too short then?
Because the remedy is like to show them how to, show bonding, swapping the charges. That's what I normally tell them to do, swap the charges.
Right, and again, right, okay. So from what we've done today, apart from swapping charges, what else can you do possibly?
I would have to think about that.
Okay, anybody else here as chemistry teachers?
So I think she can link it back to even the periodic table because that's like the basis for all chemistry stuff. So you have to link it back. They have to know that the groups that the elements fall in dictate the valence electrons, right? And that also will dictate the charges on the various ions or whatever that make up the compounds. So I think it all goes back to even that when you're looking at writing the formula, because if they miss that part, I think like everything is lost. I think it is linked. I don't know. That's just what I
No, fine. We just brainstorming it right. So one thing you can do,
Right.
I'll get to you, Anna, shortly. You could link that what you're doing back to the periodic table. And of course, again, it will mean that initially you are starting off with your monoatomic ions, basically, right? Before you get into the polyatomic ones. So you can start there, link it back to the periodic table and the idea of valency and so on. And that's one thing. Before moving on to the more sweet examples, like I like to call them, the polyatomic ones, things like your carbonate and your phosphate and your bicarbonates and so on, and writing formula of those kind of things there. So that's one thing you can do. It's not the end of it yet. Anna, see your hand, sis.
Oh, sir, I was just thinking that before I do the whole swapping of charges, I usually let them draw the bonding. Right? So they would do, say, start with sodium chloride. They would actually represent the ionic bonding, showing the transfer of electron from the sodium to the chlorine atom, right? So they will do that first, and then I will move on to like a more complicated, well, not complicated, but like a magnesium, exciting, like a magnesium chloride, right? So they see in that case that it takes 2 chlorine atoms and 1 magnesium atom there, right? Now, based on that they're drawing, they would have been able to come up with their formula. They can come up with a formula, I think, easy with the drawing, because they see that we need 2 chlorines and 1 magnesium, so it will be easier for them to say MgCl2. Now, I use that, I tell them that, hey, there's a little easier way, right? So I don't start with a swapping of charges first. I let them actually see where this swapping of charges come from. Let them do the draw it, represent the bonding, and then afterwards, I tell them that there is a shorter way that they can literally exchange the charges. So I don't know, that has worked for me and my students.
Okay, right.
Having them see the bonding first.
Yeah, man. So that is useful. You certainly want them to do some practice of getting the ionic bonds first, and then relating that back to the abstract examples of not doing it from your head, right? Without doing the bonding. And again, for me, I will just, because my background again is chemistry, I'll just take this quick moment here and just show you this little thing that I do as well. So I do, when I teach this, so I do the bonding thing first, definitely. I do swapping now last of all. Swapping is the last method I will use if the others don't work. So I do the bonding thing and I show them that happening. You can also have, of course, have them build models, right? But one of the things that I do, I learned this method many years back. I don't even recall where I learned this now. If it was from a teacher somewhere or did I see it in a book somewhere, I don't know. But I call it the hands method. And so what the hands method is, and again, this is not just for conceptual change, this is just me showing you how you can teach it also to your students. And I do the hands method as a way as well. So for example, I have ions, say like sodium, plus. Let's say take something, say like, magnesium, 2 plus, and just take 1, that's 3 plus, Al, that's 3 plus. And let's say take something, say that's fluoride, that's minus. You can take, say, chloride here, it's also minus. And say you want to take, say, even oxide, that's 2 minus. So suppose you want to combine these 2 here, right? You want to combine these 2 to make a compound. So in the hands approach, what I tell them is that the charge, magnitude, represents the hand. So Na plus is a 1 plus charge, so it has one hand. F has 1 minus charge, it has one hand. So the two hands hold, and so the formula is just NaF. Magnesium has a 2 plus charge, which means it has two hands, 1, 2. Chloride is 1 minus, it has one hand. So all hands right here, and that's that. But magnesium isn't quite happy, it only has just one hand, the other hand is free. So the next chloride, which has the next hand, and it holds. And so you can see that the formula therefore for this becomes Mg, and I need two Cls, right? So you get MgCl2. A similar thing happens with the aluminum 3 plus. So it has three hands, 1, 2, 3. Oxide, which is 2 minus, so it has two hands. So that's 1, 2. And then we join hands here. So is aluminum happy? Is the hands all occupied? No. So I need the next oxygen. But it's 2 minus, which means what? It has two hands. So 1, 2. So it has a problem again. So I need the next Al. But every time an Al comes in, it has three hands. So 1, 2, 3. Bring us O again, which has two hands because it's 2 minus charge, 1, 2. So you can see that the formula would become basically say Al2O3. All right. Other thing I do as well, sorry. So I get Al2O or 3. Other thing I do as well is for those who like math, I do what I call an LCM method. So aluminum say is Al3 plus, oxide is O2 minus. So I make the analogies like we're doing, say, math. So let's suppose I have here, say, I do math. We have x over 2 plus x over 3. In math, what's the LCM of 2 and 3?
6.
All right, thank you. Let me take out the x now. Yeah, 1 over 2 plus, say, 1 over 3. Right, so the LCM of 2 and 3 is 6. What do I do next? Having found the LCM, what do I do next?
You say how much time 2 can go into 6?
How many times can 2 go into 6, right? How many times can that happen?
3 times.
3 times, right? And how many times can 3 go into 6?
2 times.
2 times. So then I add what? 3 plus 2 and get 5 over 6.
Right.
Watch for me, please. Same thing happens here. My charges, I use that to form, right? So it's 3 and 2. What's the LCM of 3 and 2? 6. How many times can 3 go into 6?
2 times.
2 times.
2 times. How many times can 2 go into 6?
3 times.
So what's the formula? L2 or 3. Look again for him, please. Look again for him, please. Look for him, please. Look for him, please. Take something like Mg, which is 2 plus, and O is 2 minus. When you tell people swap, if you are swapping, what do you think the formula might be if you are swapping? If you are swapping.
O2, just
Okay,
like that.
Which is nonsense, right? So I don't like swapping. But
I tell them that they cancel.
okay, fine, because that is what you should be saying all along. The aim of this is to have the charges to cancel out, right?
Yeah.
So look for me, please. If I'm doing LCM, this is 2 and that is 2. What's the LCM of 2 and 2? What's the LCM of 2 and 2?
4, sir. Wait,
Huh?
2.
Not 2.
Hey, that gets me.
How many times can 2 go into 2?
1 time.
How many times can 2 go into 2?
1 time.
What does that mean for my formula?
MgO.
1 Mg, 1 O. Right?
Yeah.
Or if I take something, say like similar thing, say calcium, and I do fluoride. This is a 2 here, and that's a 1 here. What's the LCM of 2 and 1?
2.
2. How many times does 2 go into 2?
1.
1. How many times does 1 go into 2?
2.
So what's the formula?
CAF2.
Yeah, CF2. Right? And of course, if you are doing hands, when you had Mg2 plus and O2 minus, I do hands for the younger ones. Mg is 2 plus, it has 2 hands, 1, 2. O is 2 minus has two hands. 1, 2. Yeah. How many mg in O did I use?
One of each.
Yeah. All right. So I do hands. I do LCM. Or I do what I call thinking. And thinking says the aim of writing formula is to have the charges be balanced, equal and opposite, right? So I have 1 plus, 1 minus. Are the charges balanced? Yes. It's just NaF. Okay. What if I have, say, Ca2 plus and S2 minus? Are the charges balanced?
Yes.
Equal and opposite? Yes. So the formula is just CAS. Okay. Moving on. If I have, say, Na plus and I have O2 minus, are the charges balanced on the Na and on the O's?
Yes. No.
No.
No, they're not.
No. One of plus one.
I have
and
1 plus charge
minus.
and 2 negative charges. So I ask them, which one do I have more of?
Oxygen. Oxide. The oxide.
I have more
ion.
negative, right? I have more negative charge. So to balance this out, I need to increase the positive charge. Yes? So I need to add a second sodium. If I add a second sodium, are the charges now balanced out?
Yes.
So this will be Na2O. All right? And then we play. We even get to the say Al3 plus and O2 minus. Are the charges balanced out here in this case? No.
No.
Which do I have more of?
Aluminum.
I have more
Al3
positive
plus.
charges. So which means I have to increase my negative charge. But since this bond is happening between air and oxygen, I need to add another oxygen.
Maybe he's using this.
Yes, I'm using my hands.
But I write like that. No.
All right.
Zoom. The other
So
lecturer
are the charges now balanced out?
Excuse me, Dixon, your microphone is open.
Yeah. Are my charges now balanced out? No. I have 4 negative charges, 3 positive. I have to increase my positive charges. But to do that, I have to bring in the next Al. Every time Al comes in, it comes in with what? 3 plus charge. Are my charges balanced out? No. I need to bring in a next O to balance it out. So last of all, I said to you, if they still don't get this, then I say, okay, let's do swatting. You know, swap charges. But I do swap charges as my last thing on the planet. When all else fails, because some people still won't get it. It's just how life is. And because you have syllabus time pressure, you can only play for so long the different ways. Then I have to say, okay, here is a so-called easy approach, swap charges. But I don't like to swap charges because swap charges don't make you realize that the process of writing ionic formulae is about trying to balance out the charges. I want to have equal amounts of positive and negative charge. So when I finish with my formula, Al3 plus O2 minus, and I write my formula, right? By having 2 Als, each one is 3 plus. If I have 3 O's, each is 2 minus. 3 by minus 2, that's minus 6. 2 by 3 is plus 6. Have to show them the idea is to try to balance out the charges. But again, you want to make abstract concepts concrete. So you want to have them draw diagrams, have them make models, anything that you can do to try to visualize what is happening in their heads.
Sir, I also use, because some of my students like to dance, I use the flairy, you know the dance, flairy dance?
No, please. No, please show me. I don't know the dance.
No, I cannot show you. So
I don't know it.
I cannot
I don't have a
dance.
clue.
It's the swapping principle, same way, swapping from left to
I
right.
am completely unhappy.
So that is what I use, and I tell them to cancel it. I also bring it back. But I understand what you're saying. We are supposed to increase our strategies in order to bring across or to clarify the misconceptions.
Right. Try other approaches. In other words, if a child says, you, sorry, I don't understand, I'm still confused. Do not do the same thing over 3, 4, 5, 6 times. Find another approach. Yeah. Sometimes it's an analogy. So please, anybody here can help me know what is, so flurry means a SWAT? That's what you are saying? Is
Yes, in essence. Anybody know Flurry? Ding dong, I think ding dong is ding dong the
I know
artist.
of Ding Dong. I know he has many dances, but that one is the first I'm ever hearing it.
There is just a dance where they kind of swing their hands from side to side.
Is that like the most
Daniel, I
recent
really
one?
think you need to show that one though.
Yeah.
Because I don't know it either.
Really? You don't know Flurry?
I will send the link in the group.
How do you spell it? F-L-E-O-I-C. Oh, is that the one that he does? No, that's not Ding Dong. There's a guy who was a digital ad. I don't even know who that is now. All right. So please send, yeah, I will look for it because I am curious to see how that ties into chemistry. And these are the things I can say that if it can work, it could be useful. But I just really can't say that I know what this is. Let me pause this here for a while.